Hi, everybody. Thank you for joining this webinar. I am Dilip, one of the product managers at Econ Systems. Today, we are going to talk about HDR a little bit. So we'll give another minute for everybody to join, and then we'll get started. I hope you're all able to see my screen. So if you have any questions, please write down in the comments section, and we'll reach out to you. After the webinar, we'll have a separate Q&A session, and we'll handle the questions over there. So let's begin regarding HDR. So this is the agenda for today. So I'll talk a little bit about what is high dynamic range imaging and what are the different methods that are used for achieving high dynamic range imaging with different types of cameras, with different types of sensors. And there are also scenarios where some cases or applications might require HDR, which is critical for that. I'll also talk a little bit about the use cases and what type of challenges are there, especially when using high dynamic range imaging. And I'll also talk a little bit about how you can overcome them. Okay. So we'll begin with what is dynamic range in the first place. So dynamic range is basically explained as the amount of light in a scene that can be captured by the sensor. So the two major factors that limits the dynamic range or how much it can be captured by a sensor is the photodiode or the capacity of the pixel in a sensor to hold the lights. So the photodiodes operate by converting the photons into electricity. So the amount of charge that it can hold is one of the factors that limits the dynamic range of a scene. And another factor is once this charge is converted into an electron, it has to be converted into a digital signal. So there is an ADC circuit on the sensor, which it has a certain amount of bit depth. So the amount of bit depths that the sensor can support also impacts the dynamic range. So if you use a sensor which can support up to 8-bit, you can get different gradients up to 255 gradients. And if you use a sensor that can support 10 bits or even more than that, 12 bits, you can get even higher bit depths. So because of this limitation of a sensor to provide just 12 bits of information, there are ways in which multiple images or multiple exposures from the camera can be captured and stitched together to provide a HDR image. So one of the exposure is used for capturing details in the shadows, and another exposure is used for capturing details in the highlights of the scene. And they are both merged together to provide a high dynamic range imaging. So this is the most simplest explanation of how high dynamic range imaging works. And this is really helpful in scenarios because without high dynamic range imaging, you can lose a lot of critical details in a scene. For example, in an outdoor scenario, you might have a car license plate or a vehicle license plate might not be visible when you're looking at the glare from the headlights. So with HDR imaging, you are able to capture these details, and this can be life-saving in certain scenarios. Now let's talk a little bit about what are the different methods that are available for achieving high dynamic range imaging. This is one of the most basic methods for capturing high dynamic range imaging. It's called as traditional multi-exposure mode. So in this mode, multiple exposures from the sensor is captured. The biggest benefit is that you get multiple frames from the camera. So you get an exposure with T1 exposure time. Let's say T1 is short exposure and T2 is long exposure. So you get two individual frames which has the highlights as well as the bright environments in the scene. And you get the benefit of you can process this image, these two images together in software or using an external ISP or any other mechanism that you like, and combine them together. So the output of this dynamic two images will depend upon the HDR algorithm that is being used. So even though this method provides a lot of flexibility, the challenge in this method is that because you are getting two different individual frames, if there is a lot of movement in the scene, this can lead to a lot of misalignment and motion related artifacts might be visible, such as ghosting is one of the most commonly visible artifact in a multi-exposure scene. So one of the ways to overcome this limitation with multi-exposure is to use a technology called as digital overlap. So in digital overlap, this is a method that was provided by Sony. In some of the Sony sensors, it supports digital overlap HDR. So what happens here is multiple lines of the camera will be exposed at different times. So rather than providing T1 exposure frame completely and then going for a T2 exposure, so the camera starts exposing the image with T1 exposure first, and then you get a T2 exposure. So because the difference in time between a T1 exposure and T2 exposure is very short, this helps in reducing a lot of motion blur in the scene. But the challenge with this type of HDR is that this is a specific format. The readout from the sensor is in a specific format, and this has to be understood by the HDR processing algorithm. Because the algorithm needs to know how these two images can be stitched together. So the most common way to address this is by using an ISP that supports digital overlap HDR. Another method for HDR is also called as digital lateral overflow. In this DLO method of HDR, this was provided by onsemi. So in onsemi sensors, what it does is the two exposures that is used on the camera, they are both compressed by the sensor itself using a logarithmic function. So what happens in this method is that both the exposure times, depending upon the pixel value or the saturation point, they are compressed by the sensor itself and provided as a compressed output to the compressed HDR image. But this again has to be tone mapped by another ISP to be able to see all the details in the scene. So this is also a proprietary method supported by the camera, supported by the sensor, and the corresponding ISP also has to support this. In this method is also called as piecewise linear method in Sony sensors. So they are kind of similar, but they use a common methodology here. Probably this is one of the first way of using HDR. So in all the previous methods that we discussed about, motion blur was a challenge that could not be eliminated if ghosting was a challenge that could not be eliminated if motion was there in the scene. But in the case of clear HDR, this is a proprietary method from Sony, and this supports getting two different output values from the same pixel. So this is called as high conversion gain as well as low conversion gain. So the pixel supports both these modes, and you get two different outputs from the same pixel. So the photodiode will illuminate the scene for a common exposure time, and you'll get two different pixel values. And because of this single exposure that is used here, this does not induce any additional motion artifact in the scene. So that is one of the biggest advantages of this method. But the readout from the sensor is still going to be similar to the DOL method. So the ISP has to know there are two different frames coming from the sensor, and they are both interleaved together, and it has to know how to process it. Another unique way of implementing HDR on the camera is by using an architecture called as subpixel or split pixel. So this is a method provided by Sony. So Sony sensor, some of the Sony automotive grade sensors support this method for achieving high dynamic range. So basically what is present in the sensor is there are two different sizes of pixel here. So when you use a common exposure time for both these pixels, so the bigger size pixels will not be saturated immediately, but the smaller size pixels will be saturated immediately. So this can be used for achieving two different, kind of like two different exposures, but in this case it's two different individual pixels for bright scenes as well as dark scenes. And another advantage here is that this method can also support HCG as well as LCG, which was mentioned in clear HDR. So with a combination of both these methods, it is possible to provide motion-free HDR images as well as LED flicker mitigation can also be done here. So how LED flicker mitigation works is by using a longer exposure or by splitting the exposure time across a longer range so that when a LED or a digital signboard in the scene is being turned on and off due to the AC power wave, so this can be averaged out by the sensor itself. So that is one of the ways to achieve high dynamic range with LED flicker mitigation using this method. And another alternate way of achieving HDR is by using a super exposure technology from onsemi. So this allows for, this is again similar to HCG and LCG. This uses a combination of HCG and LCG along with, there will be an additional capacity for storing additional details on a same pixel. So this is more like extra details can be captured there. So when the images are saturated, especially with HCG, you can switch to the LCG mode and get more details there. And because of these additional pixels that additional details that can be stored on the same pixel, you are getting even higher dynamic range from the same sensor. So all these methods, they are all these HDR methodologies work on the sensor itself, and the corresponding ISP has to be used in all these methods to be able to achieve the best performance out of them. So these are some of the different methodologies for using for achieving high dynamic range imaging in a scene. And let's talk a little bit about in which scenarios high dynamic range can be imaging can be really helpful. One example is in sports broadcasting systems. So you might have seen in an outdoor sports stadium, one region of the scene might be completely eliminated by sunlight, and in another region there might be a lot of shadows. And in these cases, especially when you are doing some kind of analysis with the videos, for example, ball tracking or player tracking, you might not be able to see the details in the scene. So in these kind of scenarios, high dynamic range imaging can be really helpful. And also in this case, because the players are always in motion, avoiding motion blur, choosing a HDR method that allows you to eliminate motion blur can also be helpful in this scene. Another example is in agriculture, for example, autonomous tractors. The cameras are used here for analysis of the plants, how they are growing, if there are any diseases in the leaves. So all these details can be captured with HDR enabled. So sometimes the lighting in the scene can again be challenging because one side of the trees might create a lot of shadows, which does not allow you to capture does not allow you to see all the details. And especially in these scenarios, having HDR can be helpful. Also, the HDR cameras can be used for navigation of the tractors as well. For example, an autonomous tractor might want to look for obstacles in the scene and try to avoid them. So for this as well, HDR cameras can be really helpful. In a traffic surveillance system, so in this case, not just HDR, LED flicker mitigation also is really helpful because this is a classic example where there are LED signboards are there, the traffic lights can be digital, and this causes a lot of flicker in the scene. Our eyes will not be able to see this, but when you look at the details using a camera, or a driver is looking at it using a surround view camera, the details the LED might look as like it is flickering, and uh, this might not be really helpful for reading the details in the scene. Outdoor delivery robots can also be really take advantage of the HDR imaging because these robots are moving autonomously. The cameras provide a surround view of the entire setup, and it has to make sure that there are no obstacles in the scene. And if there are, if the robot is moving through a challenging intersection with difficult lighting, it has to make a critical call whether it has to cross the road or it has to wait for somebody to go, or if there are any other obstacle in the scene. So this can be really helpful for HDR can be really helpful for this scenario as well. Yeah. So now that we have seen about the different use cases where HDR can be critical, it's not really easy to implement high dynamic range imaging using the available sensors. So we'll talk a little bit about what are the different challenges there are in implementing HDR and how these can be overcome. So one of the most commonly talked about problem is because the HDR, like I explained, each different HDR methodology is supported by different sensors, and they are not compatible with all the different ISPs. And almost all the different scenarios, the sensor has to be paired up with a specific ISP that can support it to take advantage of the HDR method. So we need to make sure that we choose the sensor as well as the ISP that works specifically for the HDR method that is chosen. And the HDR method that is required for an application has to be chosen depending upon the imaging requirements for that. For example, one use case might require motion blur-free HDR, and another one might require LED flicker mitigation. So we need to choose the sensor specifically for these kind of use cases. And another common artifact that we see with HDR is motion blur or ghosting. Because we are using multiple exposures and combining them together, this can cause ghosting in the scene. And to avoid this, we can choose a HDR method that does not require multiple exposures or multiple exposure times, but rather uses a common exposure time and uses a technology like split pixel. And that can be used for eliminating motion blur. And not just the sensor as well as ISP has to be selected in a particular way. It is also important to know that the ISP also has to be tuned to achieve the best performance from the sensor. So achieving best HDR performance from an ISP requires a lot of equipment, such as you need to adjust the different lighting in the scene and capture images and tune the ISP. And this allows you to capture the details in the highlights as well as the shadows. So there is a lot of post-processing done by the ISP, and this has to be done pre-trained to the ISP beforehand. So this is called as ISP tuning, and this has to be done in a specific environment. Again, for ISP tuning, there is a lot of specific equipment that is needed. It is not always easy to measure the amount of dynamic range in the scene. So having a standardized method for measuring the dynamic range in a scene and tuning the sensor as well as ISP for that can be really helpful. For example, a standard tool like IMA test can be used for analyzing the image quality from the sensor as well as ISP after the tuning. And we can capture multiple different dynamic range images using a standard ISO chart called as OECF. So these are some of the equipment that can be used for tuning the ISP to a particular level. And especially, like I mentioned, not everybody can just take a sensor as well as ISP and make them work together. It requires a lot of expertise as well as knowledge and know-how about the sensor as well as ISP to know that how these can be tuned together. And it requires working closely with the sensor as well as ISP vendors such as Sony, onsemi as well as Omnivision, and that can also help in achieving the best performance from the sensor and ISP. So, so these are some of the methods that I wanted to discuss with you all today. Thank you all for attending. So if you have any questions, we'll discuss them now. Hi, Antonio. Nice. Thanks for joining. So I have a question from Andre. So let's say a given ISP doesn't support HDR. Can this be overcome in software ISP or a similar method? Uh, yes, Andrea, that's a good question. So there are different ways the sensor images can be stitched together. Obviously, I talked about ISP for using that. Uh, so the ISP can either be a hardware-based external ISP or it can be a software-based ISP as well. So some of the processors can support HDR images directly. So it depends upon the ISP capabilities of the processor as well. But if you do not have a processor that has ISP capabilities, of course, we can use software-based ISP as well. But in this case, it might require a lot of additional tuning to make sure that the sensor works perfectly with the ISP. Another question is, in what scenarios HDR imaging is really helpful? Like I mentioned, HDR imaging can be really beneficial, especially for outdoor-based imaging applications. So in indoor, there is usually there will be lighting in the scene. There will be controlled lighting in the scene. But the challenge with the outdoor imaging is that it's not always controlled. So the lighting can vary depending upon the time of the day, as well as depending upon the location, as well as the objects in the scene. So in these cases, HDR imaging can help you get most details out of the scene and make an image or a computer vision based on an algorithm work perfectly. Is there any a specific ISP that is considered to be superior for HDR applications? Um, I wouldn't say any specific ISP is superior. It again depends upon the type of imaging requirements. So we'll just have to choose the most common or most compatible ISP for the specific sensor or the scenario that we plan to use. Hi, Soheb. Is it possible? One question from Soheb is it possible to interface a sensor from vendor A and ISP from a vendor B? Yes, definitely. It is possible to interface one sensor from a different vendor and an ISP from a different vendor. So some ISPs are made by vendors to be compatible with many different HDR methodologies supported by the sensors. So in these cases, the ISPs can be mated with the different sensor. But it again requires a lot of tuning to make sure that the ISP works or is tuned specifically for that particular type of HDR method from the sensor. How does multi-exposure HDR affect frame rate in a video? So yes, that's a good question. So in many of the scenarios, especially with high dynamic range imaging, because we are using multiple exposures, so the number of the frame rate is actually divided by 2 if there are 2 exposures in the scene. So for example, if you use T1 and T2, you get if you are not using HDR and the sensor supports 60 FPS, and when you are using HDR, it can support 30 FPS. And if you use 3-frame HDR, you basically combine 3 exposure times together. The frame rate is divided by 3. But there are also methods such as clear HDR in which you don't really need to expose the images multiple times. So with just a single exposure, you can get 2 different images. So in these scenarios, the frame rate is not reduced. Is there any difference between wide dynamic range and high dynamic range? Uh, this is just a different terminologies for used in imaging. Sometimes it can be a bit confusing, but high dynamic range and wide dynamic range generally refers to the same thing. Is there any HDR camera for drones? Uh, how important is HDR for drones? That's a good application related question. So yes, so usually for drone based applications, what we have seen so far is the resolution also is critical for these applications because the drones are going to be flying at a high plane compared to the ground plane, and the details might not be fully visible. So the resolution is also important, and it is also important to if the drones are an outdoor based drone and it is flying in an outdoor environment for mapping or for plans or surveillance, so you might require HDR in this case. One such example from our portfolio is an 8 megapixel based HDR camera. We have an AR0821 based HDR camera that can be really helpful for drones. And also, especially for drones, the size of the cameras also has to be very compact. If the weight of the drone is high and it requires additional power requirements for lifting the payload. So you might want to use a camera that has a smaller form factor as well as a small weight. What kind of post-processing methods could make up for the lack of HDR images captured from the sensor? The most commonly used post-processing method for HDR is tone mapping. So because you capture multiple exposures and then they are compressed together, and then when you have to display it on the scene, so the display can also support only a limited amount of dynamic range. So what is usually done is it is tone mapped to support the maximum dynamic range supported by the display. Are there situations where HDR should not be used, or is it okay to always use HDR? That's a good question. So it's not really needed. For example, in robotics, in indoor robotics, you might want to, let's say, for example, a pick and place robot has to identify an object while it is moving in a conveyor belt. And these conveyor belts move at really fast speeds, like 5 meters per second or more. And in this case, when you use HDR in this scene, it's not really needed because you have enough lighting in the scene. And when you try to use HDR in the scene, you get ghosting artifacts, and that can affect the performance of the object detection algorithm or your AI-based application. So HDR is not always required. Thank you, Srikanth. Thanks for attending. Thanks for the comment. Okay. So thank you, everybody. Thank you, everyone, for joining the webinar today. I hope you found it useful, and we'll publish this webinar in our website as well as in LinkedIn so that you can watch it later as well. And if you have any questions, please feel free to reach out to us at Econ Systems. So I have shown our website as well as our email ID in which you can contact us regarding any of your queries regarding cameras or HDR or anything in particular camera related. Thank you for joining.